Back to system software. We're in the middle of looking at how functions get implemented by the compiler by translating to assembly code. Last week we looked at functions kind of abstractly in the computing world, and we looked at how we can actually implement functions in assembly. And today we're going to show how we manage variables, how we manage local variables to functions, how we generate code so that we can read and write memory locations that are associated with these variables. And let's see, homework 16. Should we go over homework 16? What's that? Oh, you did? Okay, so if you went to lab, he would have done it for you. So let's just go over quickly, kind of a quick review of function implementation. Which assembly instructions make up the prologue of the function?
The one on the prologue.
And call?
Not call.
So yeah, it's not enough to just look at this. It's the push, saving the old base pointer, setting the new base pointer, and saving the callee saved register. Now, this function has no local variables, so there's that part of the prologue is not there. Which instructions are the epilogue? Yeah.
Live, RB, eat, RC,
Yeah.
and pop, RB.
That's right. Yeah. Yeah. I don't know if the return is actually included in the epilogue or not. I'm actually not sure. So if you said either, either is fine. But this is definitely part of the epilogue, tearing down the stack and restoring the old base pointer. Oh, I forgot to pop RBX. I thought we should do that as well. Oops. Okay, what's the function call? It's call. What course? Oh, yeah. What does enter return generate? Yeah. Huh?
Move.
Which move? There's three moves here.
LR.
Yeah. So copying data into the RAX register according to our calling convention, the System 5, AMD 64 application binary interface, RAX should hold the return value when you return from the function. Questions on any of this? What's that? Oh, yeah. Questions on any of this? Okay. Okay, so let's quick review. What's a function in the computing world, in the programming language world?
Concept
Yeah.
instructions.
What's that?
Concept instructions.
Yeah, it's like a set of instructions. You can name them. There might be anonymous ones. And they have inputs and outputs. That's basically what the simplest version of a function is. How do we implement functions, but specifically ones that have their own local state and work with recursion? Yeah.
Stacks, right?
We use a stack. Yeah, we use a stack. We have, and what do we use the stack to do? What does the stack hold for each function?
Create stack frames that hold all the data associated with the given function.
And is that for each function?
For each call.
For each call to the function. So every time there's a new call, we generate a new stack frame. And the tricky part about this is that's not allocated at compile time. So we can't just decide on one memory location for the function's local variable X. We have to generate code that will make this memory location when the program runs. And that's the tricky part about implementing these functions, that we're not figuring out what the memory allocation will be at compile time. Instead, we're generating code that will cleverly do the allocation of memory at runtime when that code runs, but we're actually not going to know where or how many frames of the stack we necessarily need. Yeah?
Does, when we use malloc, does it go into the heap? That way each function call can create the exact same stack frame?
Malloc does go into the heap, but the stack is not managed by malloc. They're separate.
Well, do you think they do that so that way every single time you call a certain function, it always generates the same exact stack frame? So you don't have to manipulate it.
They do what?
Because it's the same, it's like a pointer variable that they're storing instead of all the data, and it just creates one pointer. So every single stack frame of the instance is the same.
Well, the stack frames are different for each call to the function.
For a particular function.
Even for the same function, you'll have multiple stack frames for the same function. Like in the factorial case. So when you call factorial.
They look the same.
Right, they have the same shape. Yeah, they have, yeah. So wait, sorry, what's your question?
I was wondering if they do the simple line so they could every stack could just be the same size so the compilers have to figure
Yeah, that's exactly right. Yeah. So as we talked about last time, we'll talk today. because we require, or at least in C requires the developer to tell you how many variables you have and what types they are. And that's exactly right, so that you can know at compile time very easily exactly how much space you need for each stack frame. And that does indeed make it easier to generate code that creates these stack frames. So yeah, that's exactly right. There are schemes where you do use the heap for functions as well. For instance, in functional languages where the lifetime of a function can exist past the lifetime of the stack. But that's more advanced topic if you look at how functional languages are compiled. Functional languages, functions themselves are also values that can be passed around, including functions that have been have in scope variables from their parent function. But this is kind of an advanced topic, how you actually do that, and that can involve the heap. But anyway, for our C-like functions, we use a stack. We have one stack frame activation record for each activation or instance of the call. And so we looked at last time code generation for what I might call simple functions, have no parameters, no locals, just constant return values. And we gave you this example in code gen 1, where we just have one simple IR function called main. It calls func and assigns whatever its return value is into a variable. I call this phony var because for code gen 1 you don't have to actually support variable assignment. And we have a second function here called func, which just returns 5. So if I call main, what's the return value of main? 10, yeah. So it calls func, gets the return value 5, but it doesn't do anything with it, and then just returns 10. So the approach to doing code generation was to, whenever we see this function declaration, we declare it in assembly with those pseudo-ops, give it a label to jump to, generate the prologue, and once the body is done, we generate the epilogue. That's what the exit function that Antler gives you does. When there's a call, we just generate the x86 name call, because there's no parameters here. And when there's a return, we generate a move instruction to RAX. So why do we have a move instruction corresponding to our return statement?
We can say we call it after.
Yeah, so this is the calling convention that we're given, that if you want to return a value and you want other C functions to interoperate with you, you store the return value in RAX. So this return statement does not exactly correspond to the return in the x86 world. All right, so let me step through that code generation. This is really like code gen 1. Where is... Okay, so let me step through the code generation here. Okay, when we see function main, what do we generate for function main? At compile time. So at runtime, yeah, a stack will be created, but what assembly code do we generate in our compiler when we see a function declaration main? Yeah.
We want to create the prologue of the function and move the pointers around.
Yeah. So we'll create the assembly declaration, the label to branch to, and the prologue. Okay, so that's this code here. This is what gets generated. That's right. This is what gets generated by main. Let me move this a little closer. So whenever you have main, that generates this declaration of main and the prologue. So that's enter function. in our program. Okay, what about this call? So remember, in CodeGen 1, you don't have to support return values, so what gets generated when we have a call?
Can you repeat that?
What's that?
Can you repeat that?
What gets generated when we have a simple IR call? Yeah.
You write call in the name of the.
Yeah, there's just an assembly instruction called call, and because we've used the same label as the name of the function that was given to us, we can just use that label for the x86 call. So this is the x86 call, not the IR call. Now there'll be more to do with this if once we have to deal with parameters and return values, but that's all we need to generate for CodeGen 1. And what about return? What do we generate when we have a return? Yeah. What's that? No, not ret. Yeah.
Move the value 10 to RX.
Exactly. Yeah. So remember, the behavior of return in the x86 world is storing a value to RAX because that's the calling convention. The ret is really part of the epilogue. You can't return until you've torn down the stack and prepared the stack for the return. Yeah.
So the first part of these is giving the if look, and then the other one is the look.
Yeah. You mean the enter function? Yeah, that's exactly right. So this is enter. Changed color here. This is enter call, and our return IR instruction corresponds to a move in assembly because we want to store this value in RAX, whatever that value is. The exit function happens when we reach the end of our function block. So this is the function block, and at the end of it, Antler will call exit function for us. And what happens on exit function when we're done processing, we're done compiling the entire function? Yeah.
They move to RBC off RBC.
So yeah, good memory of the epilogue. Yeah, the epilogue, which is, and I'll post it here. The epilogue, which, as your fellow classmate remembered, is restore the old base pointer. I'm sorry, restore the old stack pointer, restore the old base pointer, and then call the x86 return. And what does the x86 return instruction do? It doesn't copy a value to RAX. What does it do? Does anyone remember? What's that?
It brings you to the current pointer, the exact pointer. Basically, it takes you back to where you're supposed to be.
It takes you back to the caller, and the way it does that is it pops the return address off the stack and then branches to that address. So return, it doesn't behave quite like return in C. In C, it's taking the value and replacing replacing the callee at the caller's site, and also restoring flow of control. Return in the x86 world, all it does is pop the return address and branch to it. That's it. It doesn't do any value saving or transfer for you. That's what the move instruction does. So this is enter return. So questions on this? Questions on this code generation? Yeah.
This is like a semantic thing. You may have mentioned this, but translating in my head between MIPS and x86,
Uh-huh.
the I-type instructions are not designated with I, right? You use the dollar sign for the immediate values.
Yeah. So I-types are for immediates. Yeah, that's right. You use the different. Use a different operand. Yeah, and there's a whole bunch. There's a huge number of move instructions in the Intel world. We're going to see another one of those today. There are I was thinking you meant I add. There's integer versus floating point instructions, but that's a different story. Questions on this? So hopefully this is a helpful guide to what CodeGen 1 will do. And I've given you like the Python code for doing this. So most of this is just, let me actually take out this comment here. This is maybe not the least confusing thing. So your implementation of these 4 functions are almost entirely just going to be literally printing out this text. The only place where it's not printing out this text is when it, I guess I can't highlight, is when it, oh, I can't do that, is when it uses a name given in the IR. So when we declare a function, we ask the developer to give us the name, and we use that name in these 3 spots here when we generate the function definition and prologue in assembly. And same for the call. When we generate the call, we use whatever name was given to us in the syntax tree, given to us by the developer. And for the return as well. Whatever number was given, we just plug it in here. But all the rest of this is literally just, you just literally put that string in Python and print it in Python. In the way I show you in the just sys, you know, the, what is it, outfile.write. Yeah.
Are you able to explain the last part, the exit function?
This one?
Yeah.
The exit function?
Yeah.
Yeah, this exit function will, okay, so the reason this happens is what Antler is really doing under the hood is it's creating a syntax tree that consists of, I'm trying to remember my grammar. We have a unit as the root of the tree. Underneath a unit is a function. Underneath the function is many things. It includes the function keyword. It includes some name token. And it includes several other things, including the return. So what exit and enter do is, if you remember several lectures ago, how did we write a translation? How do we write the translation from infix to postfix using our grammar-based approach, our tree-based approach? Yeah.
You know, like you work your way, you go to the bottom and then like post order and work your way up, right?
Yeah, you traverse the tree, and when on each of these nodes, there's a rule for how you generate the output. And so you're doing the exact same thing in your compiler, except all the tree generation and rule calling is done for you. The traversal is all done for you. You just have to write instructions on what happens on each node. And so that you can do both pre-order and post-order style transformations, Antler gives you both enter, the name of the node, and exit, the name of the node. So when enter will be executed, and so there's always a tree traversal, of a complete tree traversal of the tree, you know, from left to right on the children. And whenever you enter the node, enter function is called. And after enter function is called, all of the children are processed. So the function keyword, name, locals, etc., return. And then once all of the children have been processed and we're back in the parent, then exit function is called. So this gives you this nice nested structure to function to where we can put code that comes before the body in enter and code that comes after the body in exit. Does that answer your question? So I didn't go too much into the details of Antler. I just kind of gave you the instructions, but that's what's behind enter and exit. And I think for all everything except exit function, and I'm even thinking that maybe I should have designed it so that you didn't even need exit function, but all the rest are just going to be enter, if I'm remembering right, for this IR. You won't have to ever use exit again. So you can think of it as just one rule for each node when you traverse the tree. All right, that's a good question, though. All right, questions on how CodeGen 1 works? Okay, so this is similar. I'll leave it as an exercise to you to work out or test it in your CodeGen. So this is compile time. This is what your compiler does. But the tricky part to wrap your head around is that no actual stack frames are being created here. Your compiler is literally just printing out text. It's literally just printing out this text as a string. The compiler doesn't have any understanding of what this text is. You, as the rule writer, are writing the correct assembly to output for each of these constructs. But the compiler has no sense of what is happening with this at runtime. So this is compile time. Runtime is what the computer does when it executes the assembly code that your compiler has generated. And at this point, your compiler's work is done. The compiler is not doing anything else at this point. Now it's all up to the operating system and the machine to execute your assembly code. And if your compiler is written correctly, it will execute and give you the same input and output for each function that the meaning of your input program would give as well. Does that make sense, this distinction? Compile time, this is when your compiler runs, so this is the runtime of the compiler. But we call that compile time in the compiler world, to distinguish it from runtime. That is the runtime of the output program, when the output program runs. So let's work out what this, just to illustrate again how functions work at runtime, the functions that we generated so cleverly with our stack allocation, how these work at when they actually run on the machine. Just to review what the machine does with this assembly code. Okay. All right, so in order for this to be kicked off, the C runtime actually calls main for you. That's why main is a function, because you can think of it as the system itself calling your main function. It's a little out of scope of this class, but you can just think of when you exec your program, what exec will ultimately do is end up calling main for you. So there is a stack frame effectively being set up for main. But let's just pretend that main is, there's no arguments being passed to it, and we're starting with a fresh stack. So we call main, and there's no local variables here as well. So here's our stack, and we grow downwards with our stack. We call main, and what does call do in the x86 world? What does the call instruction do? Yeah. It creates a new stack frame for the return address. So there will actually be a return address back into the C runtime. Don't worry too much about this. I have links to details if you actually want to see how the C runtime works. And then what does it do? So it pushes the return address, and then what does call do?
Calls the function.
And how does it call it? Yeah.
It pushes the pointer or up inside into the base.
Well, even before we get here, how do we get to the first instruction of main?
First tree.
Well, there's no tree here, right? This is the assembly code, yeah. Yeah, so what call is really a branch instruction. Call is very, very similar to a branch instruction. It's a branch instruction that first pushes the next address, the next IP, the instruction pointer in the Intel world, and it branches to this line of code in the binary file. Now, we talked a little bit about linking and how the executable is machine code, and there's a linker table that tells you where all the functions are. But when main is called, it's effectively a branch to whatever memory location main's instructions are stored in your executable file, which are put in memory by exec. So call will change the instruction pointer to be the first instruction of main. So now we're actually executing main. So what's the first thing that happens in main? We push the old base pointer. So let's say we have RBP is pointing somewhere up the stack right now. And when we push it, we save a pointer to the old RBP stack frame, the stack frame that it's pointing to, this kind of pseudo stack frame of the C runtime. And then what's the next instruction? And here's a pointer to our stack pointer, because after we push, we update the stack pointer to be the top of the stack. So what's the next instruction? We copy the current stack pointer into the base pointer. So this updates the base pointer to now point to this part of the stack. What? So RBP now points to this entry in the stack. It's basically the middle of the main stack frame. And what's the next thing we do? We push whatever the value of RBP is. So this is going to be the RBX. And what happens to the stack pointer after we push? Stack pointer gets updated to whatever the new. So all push does is it does a move, a store to memory, and then increments the stack pointer by the width of whatever you're pushing. So questions on this prologue, the behavior of the prologue and the stack? Yeah.
What exactly is move doing again?
Move is copying. So what's more useful, seeing arrows for pointers or actual like concrete numbers? Arrows. Okay. So let's keep arrows. Let me go through these steps one more time. So when we're here at the first instruction, before we execute the first instruction, RBP is pointing somewhere earlier in the stack, and our stack pointer is pointing here at the top of the stack. So when we push RBP, the old RBP, whatever this RBP is, gets copied onto the stack, and RSP is updated to be the new top of the stack. Now when we execute this move, it copies whatever this stack pointer is into RBP. So RBP now no longer points to somewhere up the stack. Now it points to the current top of the stack, the same place that RSP points to. It is copying whatever the value of RSP is and copying it into RBP. So if you prefer the arrow sort of pointer-based approach, that means these two have the same memory address. If this is, memory address 04, then both of these now have the value 0x0. Well, 04 is probably not a good address to use. Let's just say decimal 8. I'm just going to number these with just a decimal integer. So now both of these have the address 8. Yeah.
What's the point of pushing the base pointer originally?
Why do we save the old base pointer? Anyone remember? So we can get back to the caller's stack. We'll see that when we enter func. Was there another question over here? Okay. And then we call push RBX. That just saves the old value of this register. We're not even going to use it here, but it's required for the calling convention. Okay, so now we've finished setting up our stack frame for main. So this is main's, one call of main's stack frame. All right, what about call func? What happens when we run call func?
Calls fun.
Okay, but what are the two steps at the machine level that happens? Yeah.
First we need to set the parent address, we went to the func.
Right.
And then we branch to the func.
Exactly right. So what the call instruction, what the two steps it does in the x86 world is it saves the return address in main, which is going to be this return address. So if this is line 1, 2, 3, 4, say this is line 4, then this saves line 4. Well, this is a different memory space. So This would be something higher. Let's say it's like 104. Then it saves the address of this instruction in memory. That's what call does. It saves that, and then it branches. So if this arrow is our instruction pointer, it then branches to func, which puts us at the beginning, the first line of func. Questions on this? So here is our saved stack frame on the stack for our call to main. And this execution of call, pushing the return address, starts creating the stack frame for func. Yeah.
Where does call save the return address to?
Where does call save the return address to? To the stack. So call pushes to the stack, and all this updates RSP to be whatever the new top of the stack is. And so this is starting to construct the stack frame for func. Yeah.
So the return address is saved inside the function on the stack frame and not the main stack frame?
Right, yeah, save inside func's stack frame. Save inside the stack frame of the callee. Because we're going to have this is the calling convention. You could imagine doing this in different ways. It's probably possible. Whether you consider this part of the caller or the callee is almost irrelevant at this point. It's stored onto the stack at this point, when you first make the call. But it's considered part of the callee's stack. Okay, so let me, yeah.
I was a note not to, like when it returns, how to go call 104 again.
How to
move on to the next one.
Oh, sorry about that. Yeah, this should be like 105. So it actually stores current instruction pointer +1 at +1 instruction. So good. Yeah, that's a good point. So it actually records the next instruction pointer. I guess you could make the return add 1 to it, but I think the current x86 instruction set adds 1 to the return address to find the return address, or adds 1 instruction to it. Okay, so our stack pointer is here. Our base pointer is still on the old stack frame, on main stack frame. So what's the first thing that happens in func? We push the old our base pointer, which is here. So since you like pointer diagrams, this points to this memory location. This is what RBP, the address RBP has, 8. So this is storing the address 8 on the stack, and RSP gets updated to whatever the top of the stack is. Questions on that? Everybody good so far? And now we execute the next part of the prologue, which just copies the current stack pointer, which is pointing to address 11, and it copies that into the RBP register. So that has the effect of making RBP point to the same memory location that RSP points to. Both of these point to address 11. So these have the address in the register. The register is holding address 11. Questions? Questions on that? Okay, so then we push whatever RBX was. This is just part of the calling convention. And this updates RSP, leaving RBP to continue to point to where we just left it. We left it at whatever the stack pointer was before. This is where RBP is currently pointing to. All right, any questions on this? All right. And here we have move immediate 5 to RAX. What did this correspond to in simple IR? Which instruction? Yeah.
Return 5.
Good, yeah, this was the return. And so the RAX register is now going to hold the value 5. Doesn't do anything with the stack. You could potentially store this on a stack, but this current calling convention does not do that. And now, what part of the function is this? Epilogue, good. So what does the epilogue do? What's the first thing it does? Yeah.
It copies the RPC into the RPF or SP.
That's right. So it updates RSP to be whatever our BP currently is. This has the effect of destroying whatever this function pushed onto the stack. It's reversing this move, so you can see it's the opposite of move RSP to RBP. This is move RBP to RSP. So it undoes whatever stuff you put on the stack here. It effectively pops it. Now the data stays there, but because the stack pointer is here, any future pushes will overwrite that data. So we can think of this as tearing down the stack or popping from the stack. And then we pop RBP. What does this do? How does this change? Yeah.
It basically, with the value stored in it right now, it will move back to where it was originally, so it's going to be popping it.
Good, yeah. So what this does is it takes whatever value is at the top of the stack, which just so happens to be the old base pointer that we pushed. Because we popped all of the stuff that we put on the stack after we pushed the old RBP, and now we just take that old RBP and pop it into RBP, which has the effect of restoring RBP to be main's base pointer. Yeah. No, the top of the stack right now. So the top of the so before we started the epilogue, the top of the stack was here, and RBP was here. So when we popped this, well, when we did this move, this has the effect of popping everything off of the stack after wherever RBP is pointing to. Yeah, it effectively removes 12 because our stack pointer is now pointing lower, or well, higher in address than the stack. So you'll no longer access this through kind of official means. So now the stack pointer and the base pointer are pointing at the same spot, and this part of the stack frame is what was holding the caller's main's base pointer. So now that we're here, whatever we pop into will now have this value. So we pop it into RBP. This has the effect of restoring RBP to, it's assigning it to 8. This has the effect of restoring RBP to be the base pointer we had before we called func. Questions? Pretty good so far, I hope. And then finally, so now when we do that pop, now RSP is pointing at the return address, the stack, the entry on the stack that holds the return address. So when we call return, what return does is it pops RSP and then branches to whatever this return address is. This return address is 105, so it ends up starting restoring the instruction pointer to be this address, and then continuing to execute. That's how we restore both the stack frame and the position, the line in the main that we want to call next. Yeah.
How does RSP go from 11 to 10?
Yeah, 11 to 10. 11 to 10 is because of this pop. 10 to 9 is because of return. Return pops the return address and then branches. So just like call, so these are all inverses of each other. So call pushes the return address, then branches. Return pops the return address and then branches. And the epilogue and the prologue are like inverses of each other. The prologue pushes stuff onto the stack. The epilogue pops that same stuff from the stack, restoring the state of the pointers in the process. All right, questions? Yeah.
Every single time you pop, the stack frame moves back one, right?
Not the stack frame, but the stack frame consists of multiple entries. I don't know what you call it.
The stack pointer.
Yeah, the stack. Yeah, every time you call pop, the stack pointer adds 1 because the stack grows downwards in address space. So pushing the stack subtracts the stack pointer by 8 bytes. Popping adds 8 bytes. So 1 entry into the stack. All right, questions? Questions on that? I hope that clears some stuff out. But the main distinction here is compile time, where there's no stack frames involved at all here directly. We're just generating code. The cleverness comes from generating code that will at runtime exhibit this stack frame management behavior. That's really the hard part about compilers, is ensuring that this will happen at runtime, even though at compile time, we're not literally computing these addresses or these sets of stack frames. We're generating code that will generate those stack frames. All right, so that was the runtime behavior. So 20 minutes, get a little break. I know that's probably, maybe it's warping your head a little bit, exercising your brain a bit. Step through it, follow the instructions, and hopefully it'll make sense. And in code gen 1, I've given you the code to generate, and then you can test. You can use GDB also to step through, just test to make sure that this is what's happening at runtime after you generate the code. Okay, so let me show how local variables work. So where are locals stored? For when you have function, local, state, and C-like functions, yeah.
API.
Well, the API tells you how to store them, and in our API, where do they get stored? Yeah. Okay. Okay. So some locals are stored there. Stack, yeah, in the stack frame. So locals, strictly speaking, the locals are stored on the stack frame, and in our IR, all locals will be stored on the stack frame. So recall the ABI. I probably should have linked to the here's the ABI. So recall our ABI. We just showed this in our diagram where we have the return address, the saved RBP. The locals are stored here on the stack frame. In functions that have local variables, after the prologue, we allocate space on the stack for any local variables that we have in our function. So after that prologue, we're going to just push enough space onto the stack to hold all of our local variables. Questions on this? Okay, so let's show this example here. So remember, the stack frame is what's created at runtime, but it helps to diagram what this stack frame will look like, because as some of you correctly observed, the stack frame will have the same structure, will have the same size for our functions at runtime. So for this function, the stack frame will have, we don't have any parameters, but it will have the return address, just like before. It'll have the old base pointer, just like before. Am I forgetting anything? So return address, old base pointer, RBX, let's forget about that for now. And it'll have whatever the local variables are. And conveniently in our language, the developer has to just give us a list of the local variables. So there's 3 local variables here. And in our language, our simple IR, all the variables have the same size, all the same bit width, and they all happen to correspond to one entry on the stack frame. So all we do is we push or allocate enough space on the stack frame for each of our local variables. Now conceptually, this will correspond to var1, x, and retval. But in our generated assembly code, there's no need for actually storing these symbols anywhere. These symbols will, for instance, so x86 assembly will not process these symbols. They correspond to memory locations. But you can think of these as corresponding to the variable names that the developer gave us. But really, we're just going to allocate enough space for them and then use some clever tricks to keep track of which space corresponds to which variable when we generate code. So questions on this kind of stack frame template that we have for myfunc. So that's what the stack frame will look like. So the question is, how do we translate these ASCII strings? These are just ASCII codes. How do we translate these into something that we can use to store data during the runtime of our program? We talked about this a little last time. I don't remember. Yeah.
Yeah, you said we turn them into offsets, right?
Exactly right, yeah. So the key trick here is that because we've maintained this base pointer, we've maintained a pointer to this stack frame, we can translate these variable names into offsets from the base pointer. It's because we know exactly how many variables are going to be. We know what their bit width is. We can replace, whenever we see a usage of those variables, a store or a load to those variables, we can replace it with RBP minus some offset for that variable. And what we're going to end up doing at compile time, so this is the runtime view, but at compile time, we're going to construct a table called a symbol table that's going to store for each symbol or each variable name, it's going to store the offset from RBP. So I think the first offset's going to be -16 if I'm remembering right how I designed this. Actually, let me double check my code. Oh no, it starts at -8. It starts at -8. Oh, you can't see that. All right, so what the symbol table will hold each of our, and this is, remember, this is at compile time, it will hold a mapping from the variable name to an offset from RBP. So in our language, each of our variables is 8 bytes wide. They're all the same width. And so we're just gonna, in our compiler, keep track of these offsets for each of our variables, so that when we have assignments or usages of those variables, we'll be able to translate that variable name into a move instruction that will compute the address from looking at RBP and adding one of these offsets. They're negative offsets, we'll add them. So that's why we have this. That's why in the calling convention diagram we've got RBP -8, RBP -16, etc., corresponding to these variables. So questions so far? Questions so far on that? Yeah.
If we have a function, or if we have a variable that we use there in like the middle of the function, will the compiler try to place that variable declaration at the function?
Yeah, so that's a good question. So in our language, all variable declarations come at the top, and in the original C language, all local variables had to come first. So the compiler will just first look for all your local variables first, and then do its allocation. But it ends up being the same thing. It's just a little syntactic sugar for putting all your variable declarations at the top. In C-like languages. Okay, so the way we do this is in our function prologue, we're going to generate some assembly code that's going to give us extra space on the stack. We're going to use push, or in our case, we're going to use subtract to just subtract them all at once. And then whenever we see a usage of that variable name, we're going to translate it into computations of this offset so that we can read and write to these memory locations relative to the base pointer. So that the key trick here is that we don't know at compile time what the actual address of the stack frame is going to be, but we've cleverly generated this epilogue and prologue to make sure that RBP is always pointing to the same spot in the current stack frame. Because of that, we know that we can always use the same offsets for these variables. Okay, so that's the symbol table. Did the stack frame for this. Okay, so let's look at what assignment looks like in assembly with this scheme. So in our myfunc program, we have an assignment of x to immediate value 1. So how do we store an immediate value into a register? This is the assembly code for doing that. You say move immediate, this is the syntax for an immediate value, into a register. So now we have our value into RAX. The question then becomes is how do we move whatever the value of RAX is, and I think there's a move immediate into memory as well, but how do we move something into this offset. And it turns out that into x86 actually has a special operand you can use to do all this computation for you. So let me walk through some of the different addressing modes in x86. So what will this do? So move RAX into RBP. This will just blow away RBP. We don't want to do that. We want to keep RBP. Instead, we want to overwrite the value that RBP is pointing to. And the way you do that in the x86 world, AT&T syntax, is you put parentheses around the register. So this is basically a pointer dereference. This is a pointer dereference. This is what it looks like in the x86 world. So this will not copy to RBP. This will dereference. This will look up the value of RBP and then use that as the address for a store, a memory store. So this will overwrite whatever RBP is pointing to. Now, we don't want that either because RBP always points to, in our current scheme, always points to the old base pointer. So x86 gives us yet another addressing mode. Actually, they're really all the same addressing mode, but gives us another way, notation for doing this. And this is the notation that we're going to use. So if we want to write to a memory location that's pointed to by RBP, but has some fixed offset, we wrap RBP in parentheses and put the offset as a prefix to it. This is just the AT&T syntax of this operand, but this is just computing for you whatever RBP plus -16 is, and then going to that memory location and storing whatever your source operand is in that memory location. Questions on this? This is just the instruction set. It's their convention they use. You just have to know it. Yeah.
So it's just specifically getting the value from a different variable and storing it into the current address of
This is getting whatever the value of RAX is, the current register, the register RAX is, and storing it into the memory location that can be found by taking RBP, taking its value, subtracting 16, and then that's the memory location that's the store is going to happen to. So in x86 world, move is used for both register copies and memory stores and memory loads. In like MIPS, I think you have different instructions for that. But in x86, they're all the same instruction, you just change the operands. Yeah.
So why do we move it to RAX first? Why can't we just immediate value to?
So I think for immediate value, I think you can just do an immediate store. I do it this way when generating it because I want enter. So it's my implementation of enter assign. You could certainly do that, but I gave you the implementation of enter assign for the project, and I'm trying to be clever in writing assign. But so I wanted my sort of assembly template code to be the same for like whether it's an immediate or whether it's another variable, and so I kind of just have a Python string that holds whatever the operand is and copies it into RAX. So the problem is that you can't do a load and a store in the same instruction. If we're going to see next how to copy between variables, you have to do two operations. You have to first load from the variable and then store to the other variable that you're trying to store to. And so I just wanted the assembly code to look the same for both immediate stores and store then copy. But you could certainly, in your own compiler, if you wanted to implement enter assign yourself, you could do this in one call. Move immediate one to the memory location here you could do it that way. So, but this kind of sets up the next instruction that we want to compile when you say like x equals y. Okay, but any questions about this assembly instruction? So this does exactly what we want it to. We want to take whatever the address of RBP is, give it a fixed offset, and store or load from that memory location. You can also think of this as like an array dereference. And in fact, they're all pointer dereferences, array dereferences, they're all translated the same way. Okay, so this is what my version of enter assign, what its compilation looks like. So whenever I see x assigned to some number, I move that number into RAX, and then I move RAX into some offset from RBP, and we just look at our symbol table to figure out what number to put for the offset. So we take x, we look it up in the symbol table, it gives us negative 16, so we just place it here. And we take whatever this ASCII number is and just copy it here to be an immediate value. Yeah.
REX is just a register, right? It's not really a
It's just a register, yeah. This is a kind of general purpose register in the x86 world. I think it's historically the adder register, but yeah, this is just a register. So you could certainly do this in one instruction if you like. I did it in two. Questions on this translation? Yeah. Yeah, I think you can say move 1 into negative 16 parentheses RBP. I think that's legal to do. I'm pretty sure. Actually, I don't know. So I'm no assembly expert, just enough to write a compiler. All right, so let's see how we can compile this variation of assignment. So here we're assigning from one variable x, we're taking its value, and storing it in retval. So in our stack, we want to take whatever the value of x is here, and we want to copy it to retval. So in MIPS, that would have to be both a load and a store to make that work, and the same thing in the x86 world. I don't think you can do a load and a store in one move instruction. So how do we copy the value of an x's memory location? We use this exact same addressing mode, but in the source argument. So we look up x's offset, negative 16. We construct this operand, which takes the offset from the base pointer and gets its value from memory. And we copy it into RAX, just like we did with move immediate, but we copy whatever the value of x's memory location is into RAX. Questions on that? So this is the load, whereas if you swap these arguments, that's the store. So this is how we load the value of x into a register, temporary register. And then how do we store RAX into whatever the memory address for retval is? Move it into what?
Move it from the register into the location of retval.
Location of retval. So how do we construct the argument? Yeah.
So you do move percentage RX, comma,
Yeah.
negative 24% RBP.
Okay, good. So your classmate said move RAX to negative 24. Why negative 24? Yeah, exactly. So that's the offset that we've allocated for retval's value. So remember, we allocated enough space on the stack for each of our local variables. We record an offset from the base pointer for each of those local variables so that we don't have to know the exact memory location at runtime, but because the stack is the same size every time we call the function. And so whenever we see so I'll just show the full thing here. Whenever we see a variable, we can effectively just translate that variable. If it's on the right-hand side, we translate that into a load by looking up its offset in our symbol table and computing the operand to load its value based on that offset into a register. And whenever we have a variable on the left-hand side we want to store to that memory location, we again look up the offset in the symbol table and construct the operand to refer to that memory location based on base pointer, relative to the base pointer. And we just put it on the right-hand side for a store. So we're going to load from x, whatever its value is, into RAX, and then we're going to store that value into whatever the memory location for retval is. Questions on that? Yeah.
Basically, the destination spot is on the left.
Destination is always on the right. In the AT&T syntax world, destination is on the right, source is on the left. Probably should have made that a little clearer. But yeah, in the AT&T syntax of the Intel world, the super confusing part is if you look at Intel syntax, it's swapped. The destination is on the left, like an equal sign, kind of. This creates some ramifications for like add and subtract. But so source is always on the left in the AT&T world, AT&T syntax world, destination on the right. So we do a load of x's value and then a store to retval's value. And so that's basically all you need to do for local variables. You update your prolog to allocate space for each local variable. And you don't even really, I'll show the prolog as well, but you can just generate code that will subtract the stack pointer. And in compile time, you just keep track of which variable you want to associate with each offset for each of those memory locations that you'll push onto the stack at runtime. And then whenever you see a variable usage, at least for simple assignment, whenever it's a load, whatever it is, you look up the offset and construct this operand, this relative offset from the base pointer. And whenever it's a load, you put it on the left-hand side to some temporary register. Whenever it's a store, you put it on the right-hand side, copying from a temporary register. All right, questions on that? Okay, so let me show what the whole assembly will look like. I think I have it here somewhere. Actually, it's in CodeGen 2. Let me show CodeGen 2 before we end. Or, on second thought, it's actually not there. I'll just generate it again. So I have some debugging stuff in here, but so the top is exactly the same. We have the same prolog. Here is how we allocate space on the stack. So we have 3 8-byte entries. So we just subtract 3 times 8 from the stack pointer. That will give us this extra space onto the stack. So this is space for our locals. This subtraction is what at runtime will allocate that space. Here's our assignment of 1 to x. So in my version of enter assign, which I've given to you, we move immediate into RAX, and then we store RAX into the offset corresponding to x, which is -16. And then for our assignment of x to retval, we first load x into a temporary register, RAX, and then store into the memory location associated with retval, which we get by looking up its offset in a symbol table. Questions on that? The rest is the same because we tear down the stack by just overwriting the stack pointer to whatever the base pointer is, and that will just kind of automatically remove whatever we pushed on the stack after updating the base pointer. Questions? Okay, so CodeGen 2, I put up the project already. It's similar to CodeGen 1, except you need to support local variables and you need to support parameters. Now, I've given you the code to create the symbol table and to allocate the offset. It's a kind of a pain in the x86 world because you have to align the stack to 16 bytes for some annoying reason, and you'll get seg faults if you don't do that. So I just gave you the code to do that. So you'll have the symbol table given to you. You just have to do lookups into it, and you'll have the correct subtraction to the correct amount of bytes. That's given to you. A sign is given to you, so you can see how to test between a name and a num, how to generate code. And then you'll, function and exit function, these are the same as CodeGen 1. Call will be slightly different. We'll talk about that next time, how to pass parameters. But you'll have to generate code for we'll talk about parameters. We'll talk about parameters next time. You'll have to update enter, return, and params. But yeah, we'll cover that next time. But if you want to get started, by all means, look at this. The description's complete. And that's 120. Thanks all. Take care. Yeah.
I don't get that part.